All right, so the picture is the hard part on this problem. And first, forget about the deck. Let's just draw what this cylinder looks like. And it's this is a cylinder with its axis is the x-axis, radius is 10. And so we're just going to draw the half cylinder in question. And let's see here. Let's take it back to. Yeah. So there's this half cylinder in question. Does that make sense? Okay. Now we want to look at the part of this half cylinder that's sitting over. We've got this circular deck that's centered at the origin there in the XY plane. Yeah, okay. Let's see, radius 10. Okay, good. Well, that's good because this had radius 10. So altogether, now I'm going to have a tough time drawing the sunshade itself. I'm going to give it a whack at it, just in case I might be able to have it do a decent job. But we don't really need to draw the sunshade itself. You see why? Because we've got a formula for the surface, we've got a domain that it's sitting over, and we're going to use the graph parameterization, etc. But let's give it a try. And since it's part of this, maybe let me just pull out a different color pen here. And there's going to be kind of a it's going to be something kind of sort of like this, and of course it's part of the cylinder. So it's going to have straight line cross sections like that, but it's bent over, and of course it comes down at some sort of an angle here because it's sitting near the edge. The deck isn't very wide over there, so the sunshade is correspondingly not wide. But over here in the middle, the deck's really wide, and so the sunshade is correspondingly wide. Does that make sense? Okay. Again, we don't really need that part of the picture. All we need from the picture is the qualitative observation that on this surface, I can solve for z as a function of x and y, as per that, right? And so I can parameterize this surface sitting over the xy plane by using the graph parameterization. And I can say that x, y, z, well, I'm thinking of z, height, as a function of x and y. So x and y are my independent variables, so I call them u and v. Z is f of u comma v. Now, conveniently, there's no x's in here, so this is just going to be square root of 100 minus v squared. So there's your parameterization. That's happening over the deck. Right? Okay. All right, and we want to compute the area. So we want to compute an integral over the surface of 1 ds. That computes area. Does that make sense?
Yes.
Because in other words, we're just adding up the pieces of area themselves. In other words, we're not doing anything to it's not like we're figuring out, how much heat a piece of the sunshade is absorbing per unit area or anything like that. I'm just adding up just the areas themselves. Yeah. Okay. And now, what is ds? Well, ds is length of n. In other words, stretching factor. du dv. So I've got to take the parameterization, and again, there's a tedious little algebraic process for computing. You got to take the u partial and then the v partial and the cross product to get the n vector itself, and then take the length, which involves a square root, and it's algebraically tedious. But let's just go ahead and do that. It's not so bad. So xu is 1, 0, 0. XV is 0, 1, and then let's see, now we've got to take the v partial of this, which is negative v over the square root of 100 minus v squared. I think I might have missed a 2 in there or something. I believe that's right. Is that right? Okay, cool. And then let's see, in the cross product of these is going to be, okay, what is the cross product? Well, let's see here. It's 0, comma, and then let's see, then I have v over the square root of 100 minus v squared, comma, 1. And then the length of n is the square root, the square root of the sum of the squares of these guys. So I'm going to have v squared over 100 minus v squared plus 1, which I'm going to write this 1 squared. I'm going to write that down in a weird way as 100 minus v squared over 100 minus v squared for common denominator purposes. And altogether, that simplifies, well, I mean, the minus v squared and the plus v squared cancel, and I just have 100 over square root of 100 minus v squared. Oh, excuse me, over just 100 minus v squared. So 100 over 100 minus v squared. So altogether, that's 10 over the square root of 100 minus v squared. Is that all right?
Yeah.
Is everybody good? Any questions? Okay. Right, so let's see here. So I'm doing now an integral. Where did I go? Yeah, so I'm doing the integral of just that, du dv, over the deck. The deck is a circle of radius 10. So double integral 10 over the square root of 100 minus v squared, and then du dv. And this just is a 5.2 double integral.
So the bounds are just like into negative 10. And each one you cut first.
Yeah, which way you cut first, that's right. So it's, slice it up any way you like it, as it were. And, yep. Yep. And I don't remember the details of how this works. I'm thinking the trig substitution looks likely. And, but that should work out. Yeah. Okay. Everybody good on this one?